HyperAlloc, which is a new mechanism for reclaiming memory from virtual machines. And so the general problem we want to solve here is memory over-provisioning in virtual machines. We often have workloads that have fluctuating memory demands, like this compilation of a very large C++ code base, which has a peak memory consumption of about 16 gigabytes, but most of the time it needs less memory. And it has a total memory footprint of about 300 gigabyte minutes, which is the area below the curve. And if we deploy this in a virtual machine that is statically provisioned with 16 gigabytes for the entire runtime, we lose a lot of memory. In this case, the virtual machine occupies more than twice as much memory than the workload really needs. And this is also the case in the cloud. For example, on Azure and Alibaba, virtual machines can also be deflated by up to 50% with negligible performance impacts. And at the same time, DRAM is still expensive. It accounts for about 30% of Meta's rack costs and power consumption. So we do not only waste memory here, we really waste money. But there are solutions to reclaim memory from virtual machines. And here we generally distinguish between two modes, which I've called hard reclamation and soft reclamation. That's not very stable. No, unfortunately not. So let me quickly put this back over there. Okay. So we have two modes of operation, hard reclamation and soft reclamation. Hard reclamation permanently removes memory from a virtual machine. Soft reclamation tries to automatically reclaim unused memory, but automatically hand it back if the virtual machine needs more memory. And there are state-of-the-art implementations of these mechanisms, mainly Weird.io Balloon and Weird.io Mem, that are both integrated into Linux and QEMU. And Weird.io Balloon supports both hard and soft reclamation. Weird.io Mem, on the other side, only supports hard reclamation, because it's a manual hot plugging mechanism. In this talk, I want to primarily focus on soft reclamation because I think it's a bit more interesting. So let's take a deeper look in how Weird.io Balloon's soft reclamation mode, which is also called free page reporting, works. If you want to use Weird.io Balloon, you have a setup like this usually, where you have a KVM virtual machine that has guest virtual memory and guest physical memory and its own page allocator that manages the guest physical memory. And on the other side,
maybe just don't switch to full screen.
Yeah, maybe. I don't know. I think it's losing the monitor. Okay. So you have your virtual machine and a hypervisor and a QEMU monitor that controls the virtual machine. And Weird.io Balloon essentially consists of two parts, a guest driver and a host device, and they are communicating with each other. The free page reporting mechanism in itself consists of 4 steps. The first one is to scan the user allocator for free memory. Then, using a hypercall, the free memory or unused memory is reported back to the hypervisor or to the QEMU monitor first, which then uses mAdvice calls to issue the hypervisor to unmap the given memory. And this is actually the first major downside of this mechanism. This hypercall requires a lot of induces a lot of communication overhead, and this is what we wanted to solve with HyperAlloc. The idea is to give the host direct access to the guest page allocator, and this way we do not need hypercalls. We can directly look into the data structure and find all the free memory. This is, however, not that simple with the current allocator design because it relies on locks and free lists, so pointers. So we have control flow dependencies here. And to circumvent this, we use another allocator called LL-free. This is a lock-free and pointer-free allocator that is essentially a bit field that is updated with atomic instructions. So at the end, we replace the hypercall with atomic compare and swap operations. And what this direct access also allows us to do is to quickly report back which pages are actually reclaimed. And this way, the allocator or the guest can adapt its allocation strategy, focusing on present memory before falling back on memory that has been reclaimed. And the other problem Weird.io Balloon has is that it relies on page faults when memory should be given back to the virtual machine. Every time you access a page that was reclaimed previously, you trigger a page fault, which in turn is handled by the hypervisor, and new memory is allocated and mapped. But the problem of page faults is that peripheral devices usually do not support page faults, so this entire mechanism does not work with device pass-through. And to circumvent this, we actually require that the guest has to notify us or use a hypercall to notify the host if it allocates memory that was previously reclaimed. In this way, we do not have to use page faults. All of our map and unmap operations are explicit, and we can mirror them over VFIO to peripheral devices. We can synchronize the guest physical memory of the virtual machine with the I/O virtual memory of peripheral devices, and this way guarantee DMA safety. So much for the general architecture of HyperAlloc. Let's continue with the evaluation. We compare our mechanism against baseline Linux with no reclamation, but also against Weird.io Balloon, which supports soft reclamation and uses 2 MB granularity for this. But the hard reclamation, so manually resizing a virtual machine, is based on 4 KB granularities. And in this case, the mechanism needs a lot of hypercalls and has a very high communication overhead. This is why we also compare against an optimized version of Weird.io Balloon from Hu et al., which we've also re-implemented on a newer kernel version, that solves this communication overhead. And lastly, we also compare against Weird.io Mem, which is a manual hot plugging mechanism, so it only supports hard reclamation, but it is DMA safe like our HyperAlloc mechanism. All of this was implemented on newer kernel versions, and we have a large server that has a lot of memory. No, it's vanished entirely. Interesting.
Try to leave it in the window.
Yeah, maybe. So, we were here. Okay, so this is our test system and our kernel versions. The first thing we benchmarked is, or we evaluated the soft reclamation, and I think the most important metric for soft reclamation is the amount of over-provisioning each mechanism has. Here for the baseline, where no reclamation is activated, the memory consumption of the virtual machine only rises, and we have a total over-provisioning of 17%. 70% extra memory is used by the virtual machine, what? Oh, God. Ai. Please excuse my clumsiness. So, okay. For over provisioning, so the baseline uses about 70%. Over provisioning, Weird.io Balloon reduces this to 50%, and our mechanism reduces over provisioning to about 26%. And all of this while not increasing the runtime of the internal benchmark. In fact, we are about half a minute faster than the than even the baseline. This is because the LFA allocator has a better multi-core performance. And this over-provisioning becomes even more important if we have multiple VMs that are running for a long time. So this is what we've also measured next. Here we have 3 virtual machines that execute the same workload 3 times. And this is the combined memory consumption of all the virtual machines. And the total memory footprint here is about 14,000 gigabyte minutes. For Virtual Balloon, this goes down to 12,000 gigabyte minutes, and HyperAlloc goes even further down to about 8,400 gigabyte minutes. So, and we also have enough space in this case to run additional virtual machines, 2 additional virtual machines in the same memory envelope than the baseline. This doesn't also seem to help. So, let's continue with hard reclamation. For hard reclamation, we were primarily interested in how much we affect guest performance when we manually resize a virtual machine. And here in this case, we measured the memory bandwidth inside the guest using the Steam benchmark, which uses a bunch of copy operations and measures the memory bandwidth of each copy operations. And each dot is the memory bandwidth of a copy operation. And here we clearly see the shrink and grow phases. So there's an intense memory bandwidth impact of Virtual Balloon. This is because Virtual Balloon works with 4 kilobyte pages, so we have a lot of communication overhead here. If we use the optimized huge page version, the overhead shrinks a lot. We only see a small impact when shrinking a virtual machine and an even smaller impact when growing it. For VirtIO MEM, the impact is a bit more pronounced, and for HyperAlloc we see no impact at all. And also, if I hide the other benchmarks, we only see a few outliers, but no significant impact on the guest performance, on the guest memory bandwidth. The last thing we measured is the time we need for shrinking or growing virtual machines. For shrinking, we are about 2.5 times faster than VirtIO Balloon with huge pages and about 10 times faster than VirtIO MEM. For growing, we are even faster. This difference is even more pronounced because all of these mechanisms delay the real mapping operation to the time where the memory is accessed next, so to the page fault time, or in our case to the time where the memory is allocated. And this is why we also measured the time for the end-to-end the end-to-end time for accessing previously reclaimed memory. So this is what we see here in the last row. And here, when we access a page that was previously reclaimed, we are actually a bit slower. This is because we have an explicit hypercall mechanism here instead of a page fault, and we have an extra context switch. But the overhead is quite small, and this mechanism allows us to support DMA safety, which is what we've measured here, only against VirtIO MEM, because VirtIO Balloon does not support device pass-through. And here, compared to VirtIO MEM, we are faster in all benchmarks. So let me finish with a few words about applicability. I think if we are able to accurately estimate the amount of memory guests really need, there's a big motivation in using HyperAlloc for customers because they have reduced costs, and for providers because they have better resource utilization. But this comes with a few requirements. On the guest side, we have to switch out the page allocator, but I think cloud providers already ship custom kernels, so this is not really a showstopper. On the other side, on the provider side, we have to provide another para-virtualized device. In this case, we've implemented this in VirtIO, in QEMU. But at the end, we do not need any deeper hypervisor modifications. So, to conclude, the problem we tackled with HyperAlloc is memory over provisioning in virtual machines. We've done this by giving the hypervisor or the host direct access to the guest page frame allocator. And this way we were able to implement soft and hard reclamation and achieve DMA safety, device pass-through, and we're also much faster for shrinking and growing virtual machines than the competition. So, excuse my laptop. I hope most of it was understandable.